All right, so we start out with what is commutation. So so you have like A and B, and both of them represent observables. Then you have AB minus BA. And then if the result is 0, then those observables can be observed at the same time. But if not, then they can't. Okay, and then here we have the formulas for the position and momentum operators, whereas this is the wave function. And if you do take the commutation of the two operators, then you get the IH capital I, where the capital I is the unit operator, and we'll get to that later. And then using mathematical methods such as the Fourier transform, we can rewrite it as the position operator in terms of momentum. So here's the Fourier transform, and it's important to find the position operator from momentum or vice versa. And in this case, there's two important formulas. So here's a quick conclusion for the first part. And then here we have the position operator. So it's in respect to position. As you can tell, it's a linear in 3 dimensions. So it pretty much has 3 different components. And if one component is 0, then this line would appear as a line on a plane. And then here's what I talked about before was the momentum operator. In this case, this code is using the p-op here, and this one's real, whereas this one's just for comparison, it's the imaginary. But then if we have, instead of using p-op, we use the px3 in the code, then we have this, what we've seen in the last presentation with the momentum. And as for commutation, this is what the graph looks like if you do the real, but if you try doing imaginary, then you have something that looks like this. So, but if we look closer in, you notice that there's these bunch of almost bumpy waves there. And if we look even closer, you notice that the low points are at 0 and the high points are at 1. And what I noticed though is that the wavy fader is most likely because the Fourier transform, and the range from the 0 to 1 has something to do with the identity matrix, which is something which has to go back to the identity or the unit operator. And then here we have the example of the commutation with the S-op and px3. And as you can tell, the px3 is usually more accurate because you have this straight line at a level versus having a slope. Anyway, what we've seen in the other past slides. Here's just something that I just curious is if I want to take a graph and want to multiply it by a positive constant, and in this case I use in this case here you have there's the volume of between the two planes that intersect are actually increased because this one axis is increased if I multiply the graph by 300. But if I divide it by 300 of the normal one, then you notice that these values are smaller, so meaning that the volume between the two planes are smaller. So here's another conclusion, and then that should be it.
Okay, please join me in thanking the speaker.
So.
Joshua. Whew, I think I'm not too old, but the names often go so well. Okay, so any questions? I have a quick one, and I hope that right now everyone is nervous about their own talks, but when we go to the last talk, everyone will be relaxed and you'll get an avalanche of questions. PX and PX3. PX and PX3. What is the difference, and which of them gives more realistic commutation relation?
All right, I can't remember exactly the difference between PS and PS3, but I know that the PS3 ended up giving the more accurate results, even though in this case it's used as imaginary.
And it looks more like identity operator.
Yep.
As you declared in your initial slides. Okay, so method based on PX3 is more reliable for everything you compute. And if method based on PX and method based on PX3 coincide, it's just a wonder. PX3 is better. More questions to Joshua? 1, 2, 3. If not, let's thank him once again.